Dear student, warm welcome to NPTEL Phase 2 program video course on geosynthetics engineering in theory and practice. My name is Professor J.N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This module number 13, lecture 63, designing with geofoam. Now, I will focus the recap of the previous lecture, testing of the geofoam, which we have covered, proposed unconfined compression test, tensile properties of geofoam, proposed test specimen for tensile testing of geofoam, shear properties of geofoam, and breaking load and flexural properties of geofoam. Now, I will address the flammability test on expanded polystyrene as per IS 4671 1984. So, scope of this test, that this test classifies the rigid cellular material into self extinguishing and non self extinguishing type. This material sometimes when it come and across with the flame or the fire, and there is no existence of the geofoam material. So, it is required this kind of the flammability test on the expanded polystyrene material. So, test specimen is of size 200 millimeter, and this is 15 millimeter and 25 millimeter. And this is the EPS geofoam test specimen for the flammability test for different density. It may be 15, 20, 22 and 30. And this from here to here, this distance is 50 millimeter and this distance is 75 millimeter. So, here is a schematic representation and the photograph of flammability test on expanded polystyrene geofoam. I am just showing you with this copies. Here is the EPS geofoam material which is clamped, and this is the stand, and this is making at an angle of 45 degree. This is the 10 millimeter, this is 25 millimeter, and this from here to here is the 50 millimeter, from here to here is 75 millimeter. This is work gauge above the 125 centimeter of square. So, this act as an indicator, and from here that you are firing this geofoam material. So, you can see here this is the geofoam material, and after the firing you see, but it should cover up to the certain distance, not behind that. So, you can see that here the different density of flammability test on expanded polystyrene geofoam material. So, this may be 20, this is 15, 20, 22 and 30. So, this is EPS geofoam showing self extinguished characteristic. You can see here is a burning, and after that you can see this end up of the burning here. So, as all the geofoam sample do not burn behind the second mark, as shown here. Here is the second mark as shown here. It should not burn behind this line. So, this geofoam was found to be self-extinguished type. So, in all cases you can see whatever this is burning, it is not going behind this line. Okay? Here you can see it is not going behind this line. So, if it does not go behind this line, then that geofoam was found to be self-extinguishing type. So, here the EPA geofoam showing self-extinguishing characteristic. Now, flammability or fire, that geofoam can be considered to combustible. So, it should not expose to flame. It can be covered with the backfill soil. Some geofoam also contain a flame retardant additive to reduce the risk of ignition from fire during the construction. Because when they use for the geofoam for any construction, then there is a possibility for any firing, that is due to various reasons, and then it will be the very great problem to all of us. And now in some cases the contract has been given that contractor will be the responsible for that and he has to pay. So, one has to be very careful, and from this test only you will be able to tell that how far that fire will continue, and after that there should not be any fire, and how you can protect that also geotextile geomembrane. Sometimes that some kind of the additive also can be added, which can reduce the risk of ignition from during the construction. There are other properties also, that is thermal conductivity K. So, we use this geofoam material as a thermal conductivity. The geofoam has very good heat insulation properties. So, heat insulation is also as a function. The geofoam is a poor heat conductor as the air entrapped in it. The thermal can define as a rate of heat flow in the material, that is joule per second or watt. The unit of thermal conductivity K is watt per meter degree centigrade. This is Triaxial PA has given a chart for thermal conductivity K and thermal resistance R for various material, as you can show next, which is given by the thermal. So, before that we discussed that what is thermal properties, that is thermal resistance R. The thermal resistance is measured as per STMC 303 by D 1622 or DIN 52612 by DIN 4108. The thermal resistance can be defined as the heat flow per unit width of geofoam. The unit of thermal resistance R is meter degree centigrade per watt, and thermal conductivity K, that is geofoam has very good heat insulation properties. The geofoam is a poor heat conductor as the air entrapped in it. The thermal conductivity can be defined as the rate of heat flow in the material, that is joule per second or watt. the unit of K is watt per meter degree centigrade. So, you can see here this table, thermal conductivity K and thermal resistance R for various material. This material like geofoam and thermal conductivity K value lies between 0.029 to 0.042 watt per meter degree centigrade. And thermal resistance R, that is vary from 24 to 35 meter degree centigrade per watt. If it is a concrete, then thermal conductivity K lies between 0.9 to 1.3 watt per meter degree centigrade. And thermal resistance R 1.1 to 0.77 meter degree centigrade per watt. If it is a brick, then thermal conductivity K lies between 0.4 to 0.9 and thermal resistance R value lies between 2.5 to 1.1 meter degree centigrade per watt. If it is a plaster, the thermal conductivity value K lies between 0.3 to 0.7 watt per meter degree centigrade and thermal resistance R value lies between 3.3 to 1.4 meter degree centigrade per watt. If it is a steel, thermal conductivity K value is 46 watt per meter degree centigrade and thermal resistance R value is 0.022 meter degree centigrade per watt. If it is a iron, the thermal conductivity K value 80.4 watt per meter degree centigrade and thermal resistance R value 0.012 meter degree centigrade per watt. If it is a water, the thermal conductivity K 0.609 watt per meter degree centigrade and thermal resistance R is 1.64 degree centigrade per watt. This table is given Type-Roller PA Physics 2nd edition, Dallas, Texas, World Publisher. So, what we observed from this table, you can see that how the geofoam material can be used alternative to the concrete, brick and plaster. Most of the cases we use the concrete and the brick. So, alternatively you can use that geofoam material whose thermal conductivity and the thermal resistance, its thermal conductivity is much more lower than the concrete and the brick, and also the thermal resistance also is relatively lower than the concrete and the other kind of the material. So, this kind of the problem also I have given earlier, that how you can make use of the geofoam material as a thermal insulation and how you can save the money and also the energy. Next, chemical properties. Ultraviolet degradation. The ultraviolet causes the discoloration of the geofoam material. Geofoam is also combustible. The geofoam should be covered with soil backfill within a month. So, you cannot keep open the geofoam material in a sunlight for longer time, because there will be a problem for the UV light radiation or vandalism. So, one has to be taken care. Even then in case of geotextile material, you know that you cannot keep the open for many days. So, you ought to be cover the geofoam material within a month in order to protect from the sunlight. Otherwise, all the properties of the geofoam material will deteriorate or reduced. Biological degradation. Geofoam do not rot. Soil bacteria does not attack the geofoam. The insect can make a hole. However, additive can be added for protection. Some also in the project in USA, it has been observed that some ants has make a hole for its nest. So, then in that case there is a possibility for the failure or deteriorated of the geofoam material, but nowadays some additive can be added to protect the geofoam material from the biological degradation. Chemical resistance. Geofoam may damage due to the diesel and petrol spill on highway, railway, airfield. Therefore, geofoam is to be protected by geomembrane after installation. Geofoam is not soluble in water, so no environmental problem. However, as we can observe that when it come in contact with the petrol or the diesel, so there will be no existence of the geofoam material. So, it is always preferable that you should provide with the protection of a barrier or impermeable material like geomembrane, in order that petrol and diesel cannot directly percolate through the geomembrane to the geofoam. So, that was the reason that you should provide with the geofoam material with the geomembrane as a protection. So, every material has its own advantage and disadvantage, but we have to observe overall how we can make use of that material and safety. Oxygen index. The oxygen index OI is measured as per STMD 2873. The geofoam is combustible, therefore, it is needed to evaluate the oxygen index of geofoam, particularly for gaseous environment. A flame retardant geofoam is also available. The required minimum oxygen index of geofoam is 24%. Now, we will discuss another exciting new material, that is expanded polystyrene based geomaterial with fly ash, which we call the Epgma, and this material also newly developed in our geosynthetics research and testing laboratory. Now, this material used to prepare the Epgma, and here is the expanded polystyrene beads, this white in color, and this is the fly ash, and this is the cement. So, we are using all these three material and are producing a new exciting material which we call Epgma, or which is newly material called the geo material. Now, how to mix this? The mix ratio is defined as the ratio of two material by mass, that is EPS beads to fly ash, that is B by Fa. B is beads, Fa is fly ash. Cement to fly ash, that is C by Fa. C is cement, Fa is fly ash, and water to fly ash, is W is water and Fa is fly ash. Here mix ratio used to prepare the Epgm, that is mix ratio EPS beads to fly ash, that is B by Fa. We have taken the percentage 0.5, 1, 1.5, 2, 2.5. That means if you take the beads of about 5 gram and the fly ash is about 1000 gram, so beads to fly ash ratio will be 5 by 1000 into 100 is 0.5 percentage. Similarly, you are taking the amount of beads is 5 gram, 10 gram, 15 gram, 20 gram and 25 gram. And cement to fly ash ratio C by Fa in percentage 10, we are keeping the amount of fly ash constant, that is 1000 gram. So, we are taking that cement is about 100 gram or maybe that 150 gram or 200 gram. If the cement is 100 gram and fly ash is 1000 gram, so this ratio cement to fly ash will be equal to 100 by 1000 into 100, that will give the 10 percentage of cement to fly ash. So, like that you can take the cement amount 150 gram, that will give 15 percentage. You take 200 gram of the cement, then it will give 20 percentage. And this is water to fly ash, this percentage. So, water is 500 ml and fly ash is thousands. So, 500 by thousands into 100, this will give the 50 percentage. So, this all cases we have taken this up to 1 to 3 this 50% and later on 60% water to fly ash ratio. So, here EPS bead to fly ash is all cases is constant, only that mix ratio cement to fly ash, because we have taken 10 percentage, 15 percentage and 20 percentage, when the water to fly ash ratio is 50 percentage. Then again that EPS bead to fly ash B by Fa is same, only that cement to fly ash ratio also kept same, that is 10, 15, 20, but water to fly ash ratio has changed to 60 percentage. So, this way this mix ratio used to prepare the Epgm. So, here is the preparation of Epgm A, this is the cement and the fly ash slurry, and this is the B, that this slurry is mixed with the EPS bead. So, this is cement and fly ash, again cement and fly ash with the bead. So, this is the B slurry. Now, from this slurry it has produced the EPGS specimen casting in the mold. So, there is a mold. So, this has been cast, this specimen has been cast, and then this material has been kept in water for curing. So, you can see this is the material has been kept under water for curing. Now, we have started this investigation. This is the density EPA geofoam that after the curing. So, various days it has been maybe kept in, maybe 7 days, 15 days, 28 days like this. And this is the after this test has been performed in a UTM, this is the compressive stain and this is the compressive stain setup. This is the sample has been kept between the two plates and then load is applied. Now, from this experiment we obtained the what is effect of the beads fly ash ratio on the density of the Epgma for different cement fly ash ratio when water fly ash ratio A case is 50% and when the water fly ash ratio is 60%. So, this figure A show the x axis that beads and fly ash difference ratio. So, 0.51, 1.52, 2.5 and this is the density, that is kg per meter cube. This is the different cement by fly ash ratio, that is 10%, 15% and 20%. You can see you can have those points for different value of beads and fly ash percentage and you can have the different density when the water fly ash ratio is 50%. So, this curve is shows that density is decreasing with the increasing the beads and fly ash ratio. But when the water fly ash ratio is 60% and cement fly ash ratio also keep 10, 15 and 20%, this is x axis, that is beads and the fly ash percentage, the same 0.5, 1.5 or 2.5 and then this is the density. So, you can see the nature of the curve also is same, the density of the material, geomaterial is decreasing with increasing the beads and fly ash ratio percentage. But here it has been observed that in case of that water to fly ash ratio in 50%, the density is relatively slightly more than the when the water fly ash ratio is 60% under any density. Now, here the effect of the cement fly ash ratio on the density of the Epgma with varying the bead fly ash ratio. When the water to fly ash ratio here it is 50% and also here it is 60%. So, both the cases it has observed that cement and fly ash ratio with the beads and fly ash ratio. So, it is 0.5%, then it is increasing the bead and fly ash ratio 1.5%, 2% and 2.5%, like this it is increasing, then density also it is increasing. Also similar nature of the curve is shown in case of that water fly ash ratio also 60%. Now, here the effect of the beads and fly ash ratio and the cement and fly ash ratio, that may be 10%, 15%, 20% and we are calculating what is the compressive strength Kpa and here water fly ash ratio 50%. So, this may be 10%, 15% and 20% of the cement and the fly ash ratio. So, this compressive strength value also are decreasing with increasing the black and beads and the fly ash ratio. But in case of that water fly ash is 60%, so you can see this curve is not linear as in case of the water fly ash ratio is 50%. So, this is little bit non-linear, but overall that improvement it has been observed when the water fly ash ratio is taken 50%, because compressive strength also has more than this case when the water to fly ash ratio is 60%. So, this test also has been performed for 7 days compressive strength test of GPM, Geofoam. This is for the 7 days. Similarly, it has been performed for 28 days. And keeping all this same, water fly ash ratio here 50%, here it is 60%. And you can see that for different cement to fly ash ratio 10%, 15% and the 20%, the compressive strength value is much higher in 28 days with respect to, you can see this is for 7 days, is 7 days somewhere here below 2000, whereas in case of the 28 days it is more than about 3000, nearer 500. So, more days is giving, you are having more compressive strength value. But here also when the water then price ratio is 60%, you can see this is also the not linear, and this value of the compressive strength is lower than this case where the water price ratio is 50%. Now, this is variation of 7 and 28 days compressive strength with different bits and fly ash ratio for constant cement and fly ash ratio value and for both water and fly ash ratio. Here it is mentioned for the 7 days, 28 days and 7 days and 28 days. So, this is dotted which is 7 days. This is the relationship between the bits and fly ash ratio here, and water to fly ash ratio 60% is dotted line. This is the compressive strength. So, you can see it is a non-linear, this dotted line when the water fly ash ratio is 60%. But when the water and fly ash ratio is the 50%, that means this firm line, this is the firm line. Okay. This also for 7 days and this is for 28 days. So, you can see from here also that how there is an improvement of the compressive strength if you keep that water fly ash ratio is 50%, 7 days also it is increasing, also 28 days also it is increasing. So, after the test you can see one is the sample that post compressive strength test specimen, that what type of the failure as observed in the sample after the test. So, this is compressive strength of Epgma. This is compressive strength of the light weight fill material in kilopascal. This is bits to fly ash ratio 0.51, 1.5 to 2.5%. This water to fly ash ratio is 50%. For 7 days, cement to fly ash ratio is 10. You can see this compressive strength value of Epgma 990.8, when it is a B by FA 1% and compressive strength value 835. Then when the B by F 1.5, this 650.2, when B by F ratio is 2.0, then C by FA is 503 kilopascal, and when it is the B by F is 2.5%, this is 355 kilopascal. And when the cement to fly ash ratio is 15% and bits to fly ash ratio 0.5%, compressive strength value 1290. Then for bits and fly ratio 1 and for 15% C by FA is 1.5 kilopascal. Then for 1.5% B by F, then it is 948. Then 2% it is 781.7 and 2.5% this is 612. So, you can see here that when the beads and plies ratio with the 7 days and the cement and plies ratio increasing 10, 15, let us say 20, you can see this compressive strength value is increasing with increasing the cement and plied ratio value. It comes from 990 to 1830 for 7 days curing. Like that, you can see in all cases it is this increasing value. When this is for 28 days, cement to plies ratio percentage, let us say 10%, and this beads and plies ratio is 0.5%, and this compressive strength value 1560 for 28 days. Then when it is the cement to plies ratio value, then 2368. Then when it is the cement to plies ratio 20%, then compressive strength value 3290. For the 28 days curing, you can see that compressive strength of the lightweight fill material is dramatically increasing from 1560 to 3290. And this is the water to flies ratio for 50%. So like that, you can observe in all cases there is this improvement of the compressive strength with increasing the cement to plies ratio or the beads to plies ratio. Similarly, when the water to plies ratio is 60%, for 7 days, for the beads to plies is 0.5 and cement to plies ratio is 10%, it gives 655 kilopascal. Then when the cement to plies ratio is 15%, then this gives 1042 kilopascal. Then when cement to plies ratio 20%, it gives 1421 kilopascal. You can see that when the water to plies ratio is 60%, for the 7 days it also is increasing. This value is increasing. Even then 28 days, for the 10% cement to plies ratio, the compressive strength value 674 kilopascal. For 15%, 1507 kilopascal. For 20%, this is 2500. So for the 28 days under the 60%, this value also are increasing with respect to 7 days. But overall, if we can look here, that when the water and the plies ratio 50%, for the 28 days is give much higher value than this water plies ratio with 60%. Here it is giving, let us say 2500 for 20%, here it is giving 3290 kilopascal for 20%. Similarly, if we can see that for the 7 days it gives, when it is a water plies ratio 50%, then the compressive strength value for 20 it gives 1830, whereas for water plies ratio 60%, and this value for these 7 days, this 20% give value 1.21 kilopascal. So in all other cases you can have similar value. So overall it can be convey that water to plies ratio of 50% is superior than the water to plies ratio of 60% in terms of the compressive strength of the Epgma. Now this is the compressive stress strain curve with different cement to plies ratio and with the constant beads and plies ratio after 7 days of the curing, when water to plies ratio A is 60%, 50%, and this is B is for 60%, and after 28 days of curing, that is C, this is 50% and this is D is 60%. So here you can see here, this is the strain and the compressive strength value. So, this is for the 7 day and water plies ratio is 50% and the beads and plies ratio is 2%. This is cement plies ratio 10, 15 and 20%, 10, 15 and 20%. You can see that compressive strength value is higher, and within a very strain which may not be less than 1, which will give the compressive strength value on the hard side. Similarly, for the 7 days, but water plies ratio is 60%, you can see the nature of the curve is increasing and then reach to the maximum value and then it is this decreasing. But strain is almost less than 1%, but compressive strength value is lower than the compressive strength value for the 7 days where the water plies ratio is 50%. Similarly, this figure also shown water plies ratio is 50% for 28 days. This is water plies ratio 60% with 28 days. So, you can see this value is quite higher than with respect to this value. And here is the compressive stress strain curve with constant the cement and plies ratio and with different beads and plies ratio after 7 days of curing, when water plies ratio, this A case is 50%, B case is 60%, and after 28 days curing the C is 50% and D is 60%. You can see here also this is the strain and compressive strain curve for 7 days, the water plies ratio 50%, and this is the beads and plies ratio, this is 0.5, then beads and ply ratio 1%, beads and ply ratio 1.5%, then beads and ply ratio is 2%, like this, and beads and ply ratio is 2.5%. So, like this for 7 days, if you can compare with the water plies ratio 60%, you can say this value is much higher than this value. Similarly, for the 28 days that water plies ratio is 50%, you can see this value is higher than with respect to the 28 days when water plies ratio is 60%. Also, this strain value which is lying below the 1%. So, this is correlation between the initial tangent modulus and the compressive strain value, that is tangent modulus EI, and this is the compressive strain initial tangent. You can correlate, and EI is equal to 0.1157 sigma C plus 34.944, or R square is equal to 0.856. So, you can directly also calculate for this material what will be the initial tangent modulus if you know what will be the compressive strength of the material. So, with this equation you can use for analysis if you know what is the compressive strength of the EPGM material. So, you can directly calculate the what will be initial tangent modulus. So, this is a comparison of EPS geofoam block with EPS beads mixed lightweight fill material and the geo material. This property density that EPS geofoam block, the Horvath 1997, Murphy 1997 and Stark et al 2004, and this is Faraday and Mandel 2012. So, this EPS density is 12 to 32 and Faraday Mandel 2012 15 to 30 have performed all the tests, and this compressive strength in case of this author, it comes about 44 to 220 kilopascal, and here the Faraday Mandel got 62 to 155 kilopascal. Initial tangent modulus in megapascal for these authors is come 2.4 to 11.4 megapascal, and this is for Faraday and Mandel this 2.2 to 8.0 megapascal. Whereas this is for the EPS geofoam block, whereas in case of the lightweight geomaterial field material, this is the new material what has been developed. Here Liu et al 2006, this density is 700 to 1100 kg per meter cube, and this our study which gives 725 to 1320 kg per meter cube. And compressive strength value is case of Liu et al this 100 to 510 kilopascal, whereas in our study 158 to 3290 kilopascal. And initial tangent modulus value in case of Liu 79 to 555, and in case of initial tangent modulus in the present study 32 to 370 megapascal. So, it is quite a good value what we can obtain with this material, but we are using the all kind of the waste material like a fly ash with the alternative material which we can produce this kind of the new geomaterial, and which will be very useful in Indian condition. A new innovative lightweight geomaterial has been developed using the EPS beads, fly ash and cement, and proposed its application in various potential infrastructural projects in India. The density of the newly developed EPGM ranges from 725 to 1320 kg per meter cube, and compressive strength between 155 to 3290 kilopascal. The material can be chosen with the required density depending upon the compressive strength requirement for the proposed project. The new EPGM is approximately 4 times cheaper than the conventional EPS geofoam block material. As the geomaterial is prepared with fly ash, the disposal problem can be minimized. So, because for EPM geofoam material sometimes is very costly, so alternative to the EPS geofoam material, you can use the new geomaterial which is developed by us. Now, triaxial test on EPS geofoam. This is size of the test specimen is 750 millimeter diameter, 150 millimeter in height. So, density of the EPS geofoam used is 15, 20, 22 and 30 kg per meter cube. The shell pressure applied is about 50, 100 and 150 kilopascal. So, here is the stress strain behavior of EPS geofoam under triaxial loading condition. This is density is 15. You can see under the different this confining pressure or shell pressure, the nature of the curve between the deviated strain and the strain is the same. After a certain strain value, it is almost constant. There is not so development of the deviated stage due to the increase of the confining pressure or shell pressure. This is very typical type of the geofoam material, but most of the cases the other material soil like this confining pressure increasing, deviated stage is increasing, but in this kind of the material there is no development also the deviated stage under the different confining pressure. You can see when you have used this density of 15 kg per meter cube or 20 kg per meter cube, nature is the same, but only when it is density is increasing, the deviated stage only it is increasing. But strain value also is less, minimum strain value 2 to 3% of the strain value. Now, here is the deformation of the test specimen under different shell pressure for density of 15 kg per meter cube, 20 kg per meter cube B, and C is 22 kg per meter cube, and D is 30 kg per meter cube. This you can see before the test, this was the sample, after the test how it is deformed for 15 kg. This is the initial sample before the test, and you can see after the test in case of 20 kg per meter cube density. This is for the 22 kg per, this is the before the test, and they can see how it deformed after the test. This is 30 kg per meter cube, this is the before the test, and this is after the test. So, also we have performed more circle for different density of the EPS geofoam, and from this under the shear strength parameter also is determined under different density. When density is rho is 50, the C value is 33.75 kilopascal, pi value 1.5 degree. When density is 20, C value is 38.75, pi value is 2 degree. When density is 22 kg per meter cube, C value is 41.88 and pi value is 2 degree. When density is 30 kg per meter cube and C value is 62 kilopascal and pi value is 2.5. You can see there is a improvement of the C value with increasing the density of the geofoam material, but pi value is not so much significantly improving. That is, angle of shearing resistance is not so much improving. This is some finite element analysis using fluxing. This is the geofoam material, triaxial axisymmetric geopointing model of EPS geofoam has been studied. And this is the input parameter of test condition of finite element analysis, what density 15, 20, 22 and 30. This is the model, this is more Coulomb, and Danish condition is the 100, and these are the C value, and this is the pi value what you have obtained from here. So this value also is incorporated into the FEM analysis, and we also calculated the what is the E value of the material, and then Poisson's ratio is taken, mu is 0.1 in this case, this is 0.12 for 22, and for 22 it is 0.125, and for 30 density is 0.17. And mu, that Poisson's ratio is calculated using this equation 0.0056 rho plus 0.0024, where rho is the density of EPS geofoam is kg per meter cube. This equation is taken from EPS construction method development organization, Tokyo, Japan, 1992. These are the input data into this program, and this the figures show the correlation between the cohesion and the density of the EPS geofoam, and you can see that this density of the geofoam is increasing and this cohesion value is also increasing, and you can develop a correlation, that is equation, that is C is equal to 0.089 rho square minus 2.143 rho plus 45.78 when R square is equal to 1. So if you know that what will be the density of the geofoam material, you can directly also calculate what will be the cohesion value in terms of kilopascal. This is the comparison deviator stress obtained from the experimental data and finite element analysis. This here is the different density 15, 20, 22 and 30, and this is sigma of D, the sigma, that is deviator stress for when sigma 3 is 50 kilopascal. So this is experimentally you are having 70.61, finite element analysis gives 69.74, so variation is 1.23. So all cases you can see this is the experimental and finite element measure, this is variation, so it is well matched. So when the deviation stress also 100 kilopascal, you can see that experimental 74.26, this is 72.20 by finite element method analysis. So variation is 2.69. So not so much variation. Here when the deviator stress is 150 kilopascal, that confining pressure 156 kilopascal, then this deviator stress 76.76, and this for the finite element analysis 75.04, so variation is 2.24%. So it is well matching with the experimental and finite element method in all cases of density what we have been observed. Now this is the cell pressure for 50 kilopascal, 100 kilopascal and 150 kilopascal. This one, this is for 15 kg per meter cube, this is 20 kg per meter cube, this is 22 kg per meter cube, and this is 30 kg per meter cube. This is what will be the horizontal deformation of the specimen obtained from finite element method. This is the different density 15, 20, 22 and 30, and this is deformation when sigma 3 is 50 kilopascal, and this deformation is 3.117. When the deformation, when the sigma 3 is 100 kilopascal, deformation is 3.105. When the sigma 3 is 150 kilopascal, then deformation is 3.039. So there is not significant that any improvement of the deformation or horizontal deformation of the specimen which is obtained from the finite element method. In all cases, when the density is 20, 22 and 30, we can see there is not so significant difference with increasing this sigma 3 value or confining pressure. So summary, the deviator stress of the EPS geofoam increases with the increase in the density of the material. Deviator stress of EPS geofoam for same density of the material was found to be equal for all confining pressure. In the calculation of the shear strength parameter of EPS geofoam, it was observed that the cohesion of the material increased with the increase in the density, but a very marginal increase was observed in the angle of internal friction. Now, here is one example. EPS geofoam is used as a field material having unit weight gamma g is 0.22 kilonewton per meter cube, and allowable compressive strength sigma A is 110 kilonewton per meter square. Pavement thickness is 930. This is pavement thickness 930 millimeter is laid on the top of the geofoam. This is the geofoam material. So, EPS geofoam as shown here. So, here is the concrete, that density of the concrete is 25 kilonewton per meter cube, and this is the dBm, that is dense bitumen macadam, which density is 20 kilonewton per meter cube, and this is the base course, that gamma base course is 20 kilonewton per meter cube, and this is the sub base. So, gamma sub base is 10 kilonewton per meter cube, and this distance is 470 millimeter, that is sub base, and the base course thickness 250 millimeter, and this is dBm, that is dense bitumen macadam is 170 millimeter, and this is the concrete is 40 millimeter in thickness. So, you have to calculate the stress due to the del load on the top of the EPS geofoam. So, here is the EPS geofoam. So, you have to calculate what will be the stress on the top, that is sigma 1 is equal to summation of gamma I into Hi. So, here the top one, the density is 24, concrete 25, and this thickness is 40 millimeter. So, 25 into 0.04, that is in case of concrete, plus this is for dBm, the density of this is gamma dBm is 20 kilonewton per meter cube, and this thickness is 170 millimeter. So, here it is 20 into 0.17 for dBm. Now, next is that base course. Base course is 20 kilonewton per meter cube, and this is 250 millimeter. So, 20 into 0.25 for the base course. Similarly, for the sub base course, this is 470 millimeter, and gamma of sub base 18 kilonewton per meter cube. So, 18 into 0.47 for sub base. So, if you add, you can have 17.86 kilonewton per meter square. Now, axial wheel load P here 80 kilonewton, and rear wheel distance, this is the B, is 0.5 meter, and ground contact, this is L, which will be the 0.2 meter as the live load as shown in this figure. This is the thickness, that what we considered H is equal to 930, this is millimeter, 930 millimeter, and this angle is the alpha. So, this you know that B plus twice H tan alpha, because this is the H, and this will be B plus twice H tan alpha, and this is the L plus twice H tan alpha. So, this is making at an angle of alpha, and here is the load, axial load, that is 81 kilonewton. So, now considering this figure, that load dispersion as the two vertical and one horizontal, we have a component of twice H tan alpha. This is twice H tan alpha. So, you know that 2 and H is equal to 9.30, and alpha value is about 26.04. So, if you consider, then you can have twice H tan alpha value. H you know 9.30, 2 into 9.30 into tan of alpha is about 26 degree. So, this will give you that this value 0.92 meter. So, therefore, B plus twice H tan alpha, B you know is given 0.5 here, 0.5 plus 2 H tan alpha is 0.92. So, it will give 1.42 meter, and L plus twice H tan alpha, that is L is equal to 0.2, this is L is 0.2 plus this twice H tan alpha is 0.92, it will give 1.12 meter. So, you know this and this, the 1.42 and 1.12. Now, stress due to the live load on the top of the EPS geofoam, EPS geofoam on the bottom. So, this EPS geofoam surface sigma 2. So, sigma 2 will be equal to, at this level, this sigma 2 will be equal to P divided by B plus twice H tan alpha into L plus twice H tan alpha. So, sigma 2 is equal to P axial load 81 is given, and this is 1.42, this is 1.12, this is 1.42, 1.12, this value. So, we are substituting this value here, this is 1.42, this is 1.12. So, this will give sigma 2 value is 50.93 kilonewton per meter square. Now, total stress due to the dead and the live load sigma is equal to sigma 1 plus sigma 2, that is sigma is equal to 17.86 plus 50.93, that will give 68.79 kilonewton per meter square, which is less than 110 kilonewton per meter square. That means it is okay. It is given that what is allowable compressive stress. So, as the total stress on the top of the EPS geofoam surface is 68.79 kilonewton per meter square, which is less than the allowable compressive stress of 110 kilonewton per meter square. Therefore, it is safe. Now, this example, the determination the factor of safety against the bouncy when the EPS geofoam layer was placed at a depth of d meter below the ground surface and water table rises to 1 meter from the bottom. So, unit weight of water gamma W is equal to 9.8 kilonewton per meter cube, unit weight of EPS geofoam gamma G is 0.22 kilonewton per meter cube, unit weight of subsoil below the ground level gamma is equal to 18 kilonewton per meter cube, height of the pavement above the EPS layer HP is 0.93 meter and height of EPS geofoam above ground level HT is equal to 2 meter and water table rise R is equal to 1 meter. So, here is you can see this is the geofoam, this material, and these are all I talked, this is the ground level and this is the water level, this is R, this is 1 meter, this is D, this is H1 and this is HP, and here is the load is the 81 kilonewton. So, here pressure P and this is upward pressure is U. Okay, this is the high water level here and this is groundwater level. So, this is the solution. From the previous problem, we know the stress due to the dead load, that is sigma 1 is 17.86 kilonewton per meter square, stress due to the live load sigma 2 is 50.93 kilonewton per meter square, stress at the bottom of the soil at excavation level, that is P0 will be equal to gamma into D. So, stress due to the replacement of soil with the geofoam, when you are using this geofoam material here instead of soil you are putting the geofoam material, then stress P will be equal to sigma 1 plus sigma 2, which we have earlier calculated, plus gamma G into H1 into D. This is H1 and this is D. So, this is gamma 1 into H1 plus D, okay, because this is up to the geofoam height. So, gamma G into H1 into D. So, this is unit weight of the EPS geofoam. Now, if we can equate P0 is equal to P, P0 is equal to P. So, gamma D is equal to sigma 1 plus sigma 2 plus gamma G into H1 plus D. So, from this equation you can calculate D is equal to sigma 1 plus sigma 2 plus gamma G into H1 divided by gamma minus gamma G. So, D is equal to sigma 1 we know 50.93, sigma 2 17.86 plus gamma G is 22 into H1 is given 2 and this gamma is 18 and this is gamma G is 0.22, this will give 3.89 meter is approximately 4 meter. Now, for calculation of the factor of safety against the bouncy, only dead load has been considered, therefore, sigma 2 will be equal to the 0. So, P will be equal to sigma 1 plus gamma G into H1 plus D, because we have considered sigma 2 0. So, this is sigma 1 is 17.86 plus gamma G is 0.22, H1 is 2 and D value which we calculated here, D is 4. So, this is 4. So, this will give P value 19.18 kilonewton per meter square. Now, we know U is equal to gamma W into R. So, this gamma W is 9.81, this is water density, this R is equal to 1 is given. So, this will give 9.81 kilonewton per meter square. So, factor of safety against P by U will be 19.18 by 9.81, which will give the 1.95, that is greater than the 1.3, that means it is okay. Our design technology may be 10 years ahead, but our work ethics remains 50 years behind. So, we are like the 6 blind men who tried to define an elephant. One touched the ear and said, this is not a gigantic beast, but a lethargy leaf. Another felt the trunk and said, this is a snake. The other touched the leg and said, it is a big thumb, and so on. But we do not know what is that exactly this beast or the element. So, this subject is like that, one touch and can be able to say this is all the geosynthetic system material. It is not. So, one has to know all aspect of the geosynthetic material, then only will we know that what it is. Sorry for this kind of example. Now, here you can, this person is moving along the shore where there is a wave, and sometimes he has to face a difficult any kind of the rock, but he has to tackle and has to pass. So, this is unprecedented global challenges and the opportunity. So, we need that economic, social and the environmental challenges for the coming century, and require that innovative technology and the infrastructure, and we need that proper kind of the product development. At the same time, it is very much essential the country like us that manufacturing equipment of the geosynthetic material, and use of these geosynthetics is various infrastructure project in India. Also, we require working with the real people and making India a hub and the knowledge and the innovation. There is also one term that is forensic engineering. When the geosynthetic material is fell, so you require proper rules and regulation and law. There is a law, but there is no law of law. There should be a proper justice. So, that is the why that this forensic engineering has come up, and how this forensic engineering can be used in the failure of geosynthetics infrastructure. In the centrifuge, as you know, there is a model and model of model. Similarly, it is required law of law. And this is the opportunity and the challenges in the design and construction of geosynthetic reinforced system. So, use this geosynthetic material with confidence. We have also developed a kind of the reinforced earth house, which is bamboo house, and this is 1 BHK house. We have to go back to the rural area than the development in the urban area. So, this is kind of the more economical design and structure also have been proposed. This 1 BHK estimated cost is about coming about 50 to 60,000. Last, I go for the acknowledgement. I gratefully acknowledge the all authors, manufacturer and specifier for providing the information about paper, report, material, correspondence, personal, discussion and valuable comment. I would like to acknowledge several people worldwide who have helped me by sharing their experiences and expertise by publishing their paper on journal, conferences, workshops, seminar and magazine, which has helped me to deliver this material in its present form in this course. I would like to extend my sincere appreciation to Professor D.B. Kakkar, Director IT Bombay, for his constant encouragement, help and enthusiastic support in this program. Thanks for due to Professor A.N. Chandarkar, NPTEL Principal Investigator, and Professor K.B. Krishna Rao, HOD Civil Engineering Department, Professor B.M. Gadre, HOD CDIP of IIT Bombay, and NPTEL Officer of IIT Madras for excellent support and cooperation for preparing and deliver this lecture. I'd also like to thank my colleague in Civil Engineering Department for their support, help, and cooperation. I'd also like to thank the staff of Geosynthetic Research and Testing Lab, Mr. H.D. Rane, Mr. S.S. Kadam, and Mr. D.K. Chalke for their help and cooperation. I'd like to acknowledge CDIP staff, IIT Bombay, for their video recording and editing. I gratefully acknowledge all my PhD students, particularly Mr. Sushovan Datta, Dr. B.S. Asa, Mr. B. Ramratan Lal, Mr. Amit Padade, Mr. Mehebu Nadab, Mr. Sariput Nabagare, and Mrs. Usha Kadam for their help, support during the preparation of the slide and material used in this presentation. My special thanks also go to the reviewer of the course video material and the slide. If I do not acknowledge any author by mistake or any omission or inevitable error, please accept an apology for the same. Thanks to my wonderful wife and son for their love and appreciation, strong support, encouragement, and patience throughout this endeavor. I do hope that this video course will prove with student, design, engineer, manufacturer, and specifier engaged in this discipline of work. This course could not be complete with this research scholar of Civil Engineering Department, Dr. Asa B.S., Ramnathan Lal, Amit Padade, Sushovan Datta, Mehebu Nadab, and Sariput Nagare, and Usha Kadam. This is not at all possible without the help and support from the CDIP side, Mr. Arun Kalankar, Mrs. A. Sangeeta Srivastava, Mr. Tushar Deshpande, Mr. Devendra Parab, Mr. Bijay Khedare, Mr. Amit B. Saik, Mr. Robi Paswan, and Mr. Binayak Raut. Please let us hear from you any question. Thanks for listening.